Hello, I hope you all are doing well today. Today what we're going to talk about are magnetism examples. So this is going to delve into 7 examples that kind of go over what I talked about last lecture, but doing it with actual numerical answers so that you can kind of get a feel of how these questions will operate. All right, so the first question asks, a magnetic field exerts a force of 8 times 10 to the minus 14 newtons, which is a pretty small amount of force. Most magnetic forces are pretty small. But it's saying it's exerting it to the left on a proton moving upward at a speed of 5 times 10 to the 6 meters per second. So what's actually, well, I'll draw it in a second. And we want to determine the magnitude and direction of the magnetic field is what we want to do. So we've got a proton, and remember that with magnetism, everything that we use the right-hand rule for direction will be with positive charges. If we do negative charges, we will have to swap it. And that's because current is the flow of positive charge with convention. Okay. So if you have a negative charge, you just swap the result that you get. So let's just real quick. So it says it's so I'm just going to draw it. So we have the force is acting to the left. Okay, so the magnetic force is acting to the left on the proton, whereas the proton itself is moving upward at a speed, so moving upward at a speed of 5 times 10 to the 6. And we want to determine the magnitude and direction of the magnetic field. So what we can do is we can do this in any order we want. We can do the direction first or the force first, what the magnitude is. So the force is actually pretty easy. If you remember, magnetic force is equal to the charge times the cross product of the velocity of the charge and the magnetic field itself. This ended up reducing to this ended up reducing to with just magnitude QVB sine theta, where theta is the angle between V and B. Okay, but we don't actually know what that angle is yet, other than 90 degrees, and let me show you why. If you have the velocity moving up, and you have, so that's in the y-axis, okay, and you have the force moving left and right, that means that your magnetic field is going to be on the z-axis, basically on the in and out of the page. So the B will either be in or out. Okay, it's going to be one of the other axes, whether it's in or out, because you've already got X covered and you've got Y covered. Okay, so we know that sine of theta will be sine of 90 degrees here, because the angle between V and B will be 90 degrees, and this is just 1. So this right now reduces to just QVB, okay, because QVB times 1. And so all we need to do now is we want to determine the magnitude and direction of the magnetic field. So we just need to solve, if we're doing magnitude of the field, we do just divide this over like that. Okay? And so what we've got is this is the force, right? 8 times 10 to the minus 14 newtons. Q, so for a proton, the charge is actually going to be the same that it is for for an electron, just positive, so it'll be 1.6 times 10 to the minus 19. That's coulombs, that's newtons. And then the velocity is going to be 5 times 10 to the 6 meters per second. And when you do the math on that, you get a relatively, seemingly small field, even though it's pretty large, 0.1 Tesla. Okay, and so that's the magnitude of the field, and that's kind of how these problems work. You're given 2 of them, and you want to solve for the third one, or you're given 2, and you want to solve for the fourth one, because you're usually, you know what Q is usually. And yeah, sometimes you're given the angle between them, sometimes you're not. But the other thing we need to figure out is the direction of the field. Okay, so now this is either going to be out or into the page. We're not sure yet. We know it's not the x-axis because that's what the force is on, and we know it's not the y-axis because that's what V is on. So to figure it out, use the right-hand rule again. So remember for the right-hand rule that the basically the you have V, which is on the index finger, pointing up. You have the force pointing to the left, okay? And I know that, you know, for you it would look like this, I guess, because you're looking at the screen. But when I do this, when I have my index finger pointing up and my thumb pointing to the left, my middle finger, which is the field, the direction of the field is pointing into the page. So we know that this will be into the page because of the right hand rule, okay? And again, what this looks like, this is my index finger, this is my thumb, and then the middle finger is B. So this is your index, this is your thumb, and then this is your middle finger. So it's really easy to figure that out. And that, again, circumvents needing to use a cross product here. If you did do the cross product and you know how to do a cross product, it would also tell you that. It would give you direction as well. But in this class, we're not going to really do that much, okay? Or at all, really. Okay, so the next question then, oops, copying and pasting so I don't have to write this out. Okay. We want to estimate the magnitude of the magnetic field or the magnetic force due to Earth's magnetic field, which is pretty small, 10 to the minus 4 Tesla. And we want to do it on ions crossing a cell membrane during an action potential, right? Because in our body, we have nerve impulses, right? And they're charged. And so if they're moving, they produce a magnetic field, so there should be a magnetic interaction there between Earth's magnetic field and the one that a nerve produces while moving. And so we can actually estimate what that is. It gives us Earth's magnetic field, and it gives us the action potential here. So we want the magnetic force. So what are we going to do? We're going to do the same thing here. Okay, F equals QVB. And again, there's no angle given or anything like that, so theta will just be 90 degrees again. So the charge is going to be 10 to the minus 19 coulombs, usually what you're assuming here, unless explicitly told otherwise. V is 10 to the minus 2 meters per second. Again, we're given that. And then B is 10 to the minus 4 Tesla. And so what's the force there? 10 to the minus 25 newtons. Okay, so it's a really, really small force that we're talking about here. That's why, you know, it's a storm outside. That's why we don't go like flying around, or our body, basically why our body can work just fine in the Earth's atmosphere. You know, it's not like we're being forced to move in a particular way due to the magnetic field, right? It's a really, really small force that we're talking about. All right, number 3. An electron travels at 1.5 times 10 to the 7 meters per second in a plane perpendicular. So perpendicular, that's our code word there. That's annoying. That we're going to have sine 90. Ooh. We want what will So an electron travels at 1.5 times 10 to the 7 meters per second in a plane perpendicular to a uniform field, which is 0.010 Tesla. We want to know what will the radius be, or what will be the radius of its circular motion while in the field. So if you remember, an electron while traveling in a field, or a positron, or any charged particle moving in a constant field like that, will end up just moving in a circle, right? And so we want to just know what is the radius of that. Okay, and so what we can do is, if you guys remember the equation that I wrote before, where it was basically this, and then you can velocities on both sides. So what we got was this. QB equals mv over r, and we can just solve for r. So I'm going to multiply that over and divide that over, and what we end up getting is r equals mv over qb. And what we can do is just kind of plug in. We're told that it's an electron, which means its mass, and this will be given on, you know, an exam or whatever. 9.1, I think it's 9.11, but whatever, this is accurate enough. 9.1 times 10 to the minus 31 kilograms. The velocity is 1.5 times 10 to the 7 meters per second. And the charge, 1.6 times 10 to the minus 19 coulombs, because it's an electron. Don't worry about the sign here. And the magnetic field is 0.10 Tesla. And so when you put all that together, because we're looking for a radius, if you use kilograms, meters per second, Tesla, and Coulomb, all of the units will cancel except for meters, and so you're going to be given a radius in meters, which will be a relatively small radius of 0.85 times 10 to the minus 2 meters. Okay, so pretty small radius. We wouldn't really expect, you know, a large radius. We're talking about things that are really small, right? Like electrons and all of that. Okay, so what's the next example? The next example is, if I can copy paste correctly, and again, if you know, I'm going too fast or anything like that, feel free to pause, rewind, whatever. So a wire is carrying a steady, and when you see steady, like this is pretty much every time we're going to do this, so we're not going to do anything with AC here, but this means DC current, which means it's just a constant current flow. 30 amps, okay? Has length 12 centimeters between the pole faces of a magnet, producing a uniform field of 0.90 Tesla. And if the wire is at an angle of 60 degrees, so we're finally given an angle here, to the field, what is the magnitude and direction of the force on the wire? So if you remember, anything that has a moving charge in this, moving charge produces a magnetic field. And if it is producing a magnetic field and it's within a field, it will have a force due to that. And we want to know the force of the field on the wire, because the wire is producing a field of its own. So the very first thing I want to do here is probably draw it, because I really have no idea what's kind of happening. And so all we're really told is that it's basically a magnet, the pole faces of a magnet producing a uniform field. And so really all that is setup. We just need an excuse to have a constant field. And so you can kind of draw the constant field however you want. I'm just going to do left to right, but you could do right to left or up, down. It doesn't necessarily matter. And so we've got this. But what you've also got is you've got a wire. And it says the wire is producing, or is 60 degrees to the field. And when you're drawing it, this is the only part that matters, is that you draw this wire 60 degrees to it, okay? And because of convention, it's going to be, you know, you move counterclockwise, right? So this is the direction of the current flow, because the current flow is what matters here. The current flow is what's producing the field, and they tell us the current flow, they say the wire, but that means the current flow is 60 degrees to the field. So the equation for this, if you guys remember, was we had a situation where it was another cross product, and we're using the vector of current, meaning just because the current has direction, right? And so we had a cross product here, and this also reduced similarly to the QVB, okay? And so we can do this just to get the magnitude, and we don't have to deal with a cross product. So if we just want the force, we just plug everything in. So they told us 30 amps for the current, L. They told us 12 centimeters, so that would be 0.12 meters. Make sure you use centimeter or meters for everything. So it's amp, meters, Tesla, coulombs, all of that. 0.90 Tesla was the field, and then it was sine 60 degrees, which is 1/2. So you plug all that in. What do you get? I got 2.8, and if you use all the standard units here, you'll be left with 2.8 newtons. Okay, it's really storming out there. Okay, so now we need direction. Now everything that we've done up until this point, the direction has been, everything's been perpendicular, right? But it works for 60 degrees too. So how this works is, again, you do the same thing. You do I, which is, for this one, I is in the direction of V, and it points at an angle of 60 degrees, right? And then it tells us that the field, so that's the middle finger, is to the right. Okay, you can also, again, do it to the left, and you'll get the right thing here. And so this moves like this. So my middle finger is pointing to the right, my right, okay? And so again, try this at home. Do it with, your right hand. Make sure you are trying it. And so I'm pointing diagonally. And my direction of the thumb is the direction of the force, which is into the page, okay? And so direction is into the page. And of course, the symbol for that was the X, okay? And for this is via the right-hand rule again. And you could do the cross product, right? If you want to learn how to do it, but you don't have to, right? We're not doing it. I say that every time. But yeah, that's how that type of problem works, okay? So it's very similar to QVB. And you'll see this is the majority of how problems work. You kind of just plug in, solve for the one you're missing, and then use the right-hand rule to get the direction. That's pretty much how all of magnetism works in this class. So the next one is so this one, instead of dealing with force and stuff, this one's going to be dealing with the field itself. So an electric wire in the wall of a building carries a current of 25 amps upward. And we want to know, what is the magnetic field due to this current at a point P 10 centimeters due north of the wire, okay? And so we just want to know, what is it? So it's only asking for magnitude. It's not asking for direction here. So what is the magnetic field due to this current at a point P 10 centimeters north? Okay, so we have a wire that's carrying a current. And we just want the magnetic field from it a certain point away. And if you remember, the equation we had for that was this equation where mu naught was, again, the magnetic permeability. It's just the constant similar to epsilon naught for the electric field. This is the current through the wire. 2 pi, okay, that comes out when you're deriving it. And then R means a distance, 10 centimeters away in this case. So all we really need to do is plug everything in. I know these are weird units. Tesla meter amp, and then the amps, so the amps cancel. Tesla, the 2 pi actually cancels down here, 2 pi, 4 pi. But if you plug all this in your calculator, and again, I converted the R, okay? what you end up getting, or at least what I get, is 5 times 10 to the minus 5 Tesla. Okay. And yeah, that's pretty much it. You just plug in. It's not inherently complicated. It's not as bad as some problems, okay? The next one, and we've only got 2 more to go. This guy. We have 2 parallel straight wires, 10 centimeters apart, carrying currents in opposite directions. Okay, so current I1 is 5 amps, and it says it's out of the page. And current I2, 7 amps, and into the page. And we want to determine the magnitude and direction of the B field halfway between these wires. So the very first thing we should do is draw it. Okay, so we have current I1, 5 amps, out of the page. So how I draw that is I just kind of do this. Oh, whoops, out of the page. Sorry, I'm an idiot. Dot is out of the page. And so this would be I1 equals 5 amps. And these guys then are 10 centimeters apart, but we want it halfway between, so I'm just going to draw a little this and label it 5 centimeters. And this is the area where we want the B field. Okay. And so this will produce B1. You then have this guy right here. Let me use different colors. Let's use, I guess I've got green up here. B2. This would also be 5 centimeters. And this guy is into the page. Okay, so I2, 7 amps, into the page. We want to determine the magnitude and direction halfway between. So, let's go ahead and just start with the direction. Okay, direction matters in this case. Well, actually, let's do direction last. Let's do the magnitude first. So we're going to do what we did in the previous problem, where it's just this equation, but twice. So B1 is a function of mu naught, like they all are, I1 over 2 pi R1. And this, again, is 4 pi times 10 to the minus 7, here, R1, R2. Let me fix that, that's annoying. Okay. I1 is 5 amps. 2 pi, and this is 0.05 meters. And this is equal to 2 times 10 to the minus 5 Tesla. B2, you write the same thing. Whoops. Man, it's really raining a lot down outside. 2 pi, and again, this is 0.05 meters. And this equals, not the same thing because they're different currents, 2.8 times 10 to the minus 5 Tesla. Okay. So, we've got these 2 fields. And what we need to know is their directions. Each of them produce a different direction. We need to know what they are so that we can either add or subtract. Okay? And get the total direction, right? So if you remember right, use the curling right hand rule this time. So you're not using 3 fingers right hand rule, you're using the curling one. So if we go up, we see the first wire is out of the page, okay? So out of the page means it curls around this way. So I point it towards myself and I curl it around. So what that means, what that looks like then, is the direction is going to be curling around. And if you're curling around it, at the point tangent to this curve here, it'll be perfectly to the right. At the tangent point right here, it'll be perfectly up, and then left, and then down. And for the other wire, it actually rotates in the opposite direction using that right hand rule. So we see at the point in between, they're both pointing straight up. And so they'll both add together. So what we get then is the direction, or the, hold on, total B is going to be B1 plus B2 because they're in the same direction. And so that was 2 times 10 to the minus 5 Tesla plus 2.8 times 10 to the minus 5 Tesla, which, you know, I can add 2 and 2.8, that's 4.8, times 10 to the minus 5 Tesla. And the direction, as we just saw, what the hell happened there? The direction is up, okay? And again, I use the right hand rule for that. So make sure you can do the right hand rule for both the wire and again for this type of wire, and then for QVB as well, this one. Okay? Okay, so the very last problem we have is the two wires that are interacting with each other. So there's not too many types of problems that you'll see when it comes to magnetism. I mean, these are pretty much it. These are pretty much all the main examples. Okay. The two wires of a 2-meter long appliance cord are 3 millimeters apart. We got to make sure we get our scientific notation right on that when we convert. So they're 2 meters apart, or 3 millimeters apart, and carrying a current of 8 amps, both of them. We want to calculate the force one wire exerts on the other if the currents are in opposite directions. Okay, so how we do that, and again, because they're two wires that are apart, they do exert a force on one another, okay? Because they're both producing opposite fields in this case, because they're opposite directions. Even if they were in the same direction, they'd still be affecting each other, much like this is. But we didn't calculate the force in this one, we just wanted the total field. Okay, so we don't necessarily need to draw this one. We could if we wanted to. All we know is that they're 3 millimeters apart. Oops, can't draw for the life of me. And that they're the currents are in opposite directions, so one could be up, one could be down. We're not really sure. They could be in and out. They could be left, right. We don't really know, but we don't need to. We just need to know they're in opposite directions because that tells us if the force is repulsive or attractive. Okay. Oh my God. Every time I set my hand on the tablet, it moves it. Okay. So the equation for this type of thing where you have dual wires and you want to know the force between them is mu naught, okay, how it permeates through the air, the magnetic field, or through a vacuum, I should say. You have I1, so it's a function of current 1, current 2, the length between them. Yeah, it's technically that. Or the, not the length between them, the length of the second wire specifically, because we want the force one wire exerts, I should say, wire 2. It doesn't matter in this case because they're the same length. The force wire 1 or wire 2 exerts on wire 1. Just being a little more specific here. But it doesn't matter because they're the same length. But it would be the length that you put here is the length that's affecting the other wire. And then this would be 2 pi, and then the distance between them. And so when we plug all that in, again, it's 4 pi. Oops. Can't times 10 to the minus 7 Tesla meter per amp. This is just 8 amps. 8 amps, that's their current in each one, right? Carry current of 8 amps. And then the length of 2 meters right there. And it's 2 pi. Distance between them is 3 millimeters. So it's millimeters, so centimeters times 10 to the minus 2, millimeters times 10 to the minus 3 meters. And you do all that math, I got 8.5 times 10 to the minus 3 newtons. So it's not like these wires are going to be, throwing the other wire through the appliance, right, and just pushing it fully away. There's a slight force there, but the integrity of the materials and all of that really prevents any issues. Okay, the other thing we needed to know is we want, I should be more explicit here, calculate the force magnitude and direction. And it says if the currents are in opposite directions. So opposite directions means repulsive. So if currents are in op directions. Okay. If they were in the same direction, the wires would be attracted to each other. Okay. And that's pretty much it. That's all the examples. I'm not going to extend this lecture any more than I need to. It's already 31 minutes long, 32 almost. So have a good day, and I'll see you in the next one.